All right, how you guys doing?
Wonderful.
Cool. Okay, so today we're going to be talking about bipolar junction transistors. Bipolar junction transistors are one of the most important types of devices in electronics. They have a whole lot of uses on their own, and they form the building blocks of many other components, as we'll see. So we're going to be spending a couple of days on these. We're going to start off talking about them today. We're going to just talk about their characteristics a little bit about how they're made. You guys will get to do a few measurements to see how they work. Then next time we'll do a lab where you get to use them as switches, just turning things on and off. Then after that, we'll get to use them as an amplifier, I believe. And then I believe there's actually one more lab too, where we use them to drive motors. Okay? So we're going to be spending a little bit of time on these, but today, like I said, we'll just get introduced to them and learn a little bit about how they're made and how we can test to see if they're good. Okay? And we'll get to see some data sheets as well. We'll look up a little bit of information and learn a little bit more about them that way too. We're going to start with a review of voltage multipliers and charge pumps that we talked about last time. And then we'll go on and we'll talk about BJTs. So we'll talk about what they are, why they're so important, and then how they work. So when we talk about how they work, we'll get into a little bit about how they're made, and then what that can tell us about how they actually function. For the lab, like I mentioned, we're going to be doing some measurements of the transistors themselves. So we'll see that the multimeters actually have a little section specifically made for measuring transistors and measuring their gain. We'll see where that is and how to use that. And then we'll see that transistors also behave like diodes in some ways. So we'll see how we can use the diode measuring mode in the meters to check our transistors as well. And then finally, I'll tell you a little bit about data sheets and where to find them and how to read them. Okay? Any questions before we get started? Cool. So then let's start with a brief review of voltage multipliers and charge pumps. Okay? So we said that voltage multipliers, well, I could talk about it, but we had some homework related to voltage multipliers and charge pumps. So anybody started on the homework a little bit? Not really? Anybody want to pick one that looks hard?
Let me see if I do.
5, 6, 4.
Number 4. Okay. What page was that again?
537.
All right.
That's a clipper and clamper.
Yeah, that one was the clipper and clamper homework.
I see that too.
We didn't have them. You just said it was the waves.
Oh yeah, we have
Oh, this is
quiz.
clipper
There we
and
go.
clamper. Where's the charge pump?
Okay.
I did not start with that.
Okay, I thought we had some of that. Okay, never mind. Well, that makes it a little easier then.
Nice.
Sorry, I freaked everybody out.
I was worried.
Yeah. All right, I'm sorry about that. All right. So the basic idea with clippers and clampers, right? With voltage multipliers and charge pumps. Yeah, I'm getting off to a good start. The basic idea with voltage multipliers and charge pumps was that they were ways of creating high voltage DC electricity, right? So voltage multipliers, did they start with AC or DC?
AC.
AC, exactly. So they started with AC and they put it through a voltage multiplier circuit, and basically the circuit would charge up some capacitors. And by charging up several capacitors in a row, it was able to take that AC and actually increase the voltage and turn it into a high voltage DC value. So charge pumps did basically the same thing, but they didn't start with AC. What did they start with?
DC.
DC, exactly. So they started with a DC voltage, and then they would use a little chip to essentially create artificial AC. So they had a little chip that would create a square wave on and off, which is kind of like a low fidelity AC signal. And they would use that square wave to charge up the capacitors and create the DC voltage pretty much the same way that the voltage multipliers did. Okay? So the basic idea was that they would take lower voltages and turn them into high voltage DC. So what were some of the uses for voltage multipliers and charge pumps? What's that?
Camera flash.
Yeah, camera flashes.
Oh, taser.
Tasers, yeah.
Railgun.
Tesla.
Stun guns. Tesla coils are interesting. They actually they have a number of different components in there that result in high voltage. They're not exactly voltage multipliers, but they have some amplifier circuits at the beginning, and then they have a very, very large transformer at the end. Yeah. So basically with a Tesla coil, you have a
coil on top.
right, a primary coil down here at the base. So this would be the base here. You have a primary coil there, and then the part that comes up in the middle is called the secondary. This actually has lots and lots of little windings going all the way around this coil. So this is the secondary coil, and then often they have one of those toroids on top. So basically, you have a lot of, a decently high AC voltage going around the primary coil, and then that creates a much, much higher voltage in the secondary coil, and then that ends up creating sparks coming off of the toroid at the top. So it's also creating high voltage, but it's not quite the same. So anyway, and if anybody is interested in Tesla coils, we actually have a musical Tesla coil which is not working right now. We need to do some troubleshooting on it and try and figure out what's wrong. So if anybody is interested, let me know and might be able to work on it.
Is that one that you guys got last year?
We got it several years ago.
Or a couple
Yeah.
years? Okay.
Yeah. Anyway.
Might be interesting.
Yeah.
How is it musical? Is it hooked up to like an instrument or?
No.
Right. So the frequency of the spark creates different tones, and what happens is that there's actually a little box that has not MP3s, but little musical songs recorded on a chip, and then that box sends signals over to the Tesla coil to make the sparks happen at different frequencies.
That's so cool.
Notes. Yeah.
Because all music is a frequency.
Oh man,
Yeah.
that'd be cool.
Yeah. So anyway, so that's a brief review of voltage multipliers and charge pumps. Questions about that? Okay. So then let's go on to our lecture. So what is a bipolar junction transistor? They're called BJTs for short because bipolar junction transistor is a big mouthful. So BJT is a silicon-based device where a small current controls a large current. Yeah.
So it's like a relay?
Kind of, yeah. So A relay is an electronic switch, and you have a small current that goes in, and it basically closes the switch and then allows a large current to go through. So transistors, BJTs, can be used in a similar way. You can have a small current going in that allows a large current to go through. So in that way, they're similar. There are a couple of differences. So with a relay, you have a physical switch inside there which moves, and when it's not touching, there's no current flowing. When it's touching, it actually allows the current to flow and makes a low resistance path. Transistors are a little bit different. Transistors are just made out of silicon, and we'll see how they're made in a minute. But they're made out of silicon, so they have no moving parts. So we call them solid state devices. Basically, they're a solid block. Nothing moves in there. So the way that they control the current is a little bit different. We'll see it has to do with the physics of the silicon. A small amount of current going in one place allows a large amount of current to flow through in a different way. So they're solid state, they don't have any moving parts, and then also transistors can be turned partially on and partially off. So relays are only on or off. They're digital.
Yeah.
Transistors can be used in a digital way, but they can also be used in an analog fashion, where they're partway on and partway off.
So they can let only a certain amount of current in?
Yeah, yeah, exactly.
They don't have to let the full force, they can just let part, oh,
They
okay.
can just let a small amount.
And that's dependent on the small input current? Small,
Yeah, exactly. So,
wow.
so when you use them in the on-off digital mode, you can use them just like a regular switch to turn on a light or turn on, a motor full force. When you're using them in the analog mode, you can use them to turn on a motor part way if you want, or make a light dim, or more often actually they're used to amplify very small signals. So, yeah.
How fast can they be switched on and off?
Very, very fast.
Really?
Yes.
Ooh.
Yeah. In the radio frequency, so
Okay.
in the megahertz to gigahertz range.
Nice.
So that's another difference. Relays have a finite on-off time because it's a physically moving component. It's a piece of metal that has to move from here to here. So that takes a finite amount of time. Probably on the order of 10 or 20 milliseconds. So whereas the transistors can be switched on and off, like I said, millions to billions of times a second. So
Wow.
they're much, much faster. Yeah. So that's why they're able to amplify radio signals. So, yeah. Okay, so that's what a BJT is. Some of the reasons that we care is that BJTs and transistors make up the building blocks of pretty much all electronic devices that are out there today. So they can be used in digital devices, in things like computers, phones, cameras, calculators. Any type of digital chip is based on transistors that are turned on and off. So transistors are used in the processing. They're also used in memory. So when people talk about computers storing a bunch of ones and zeros, what they're really talking about is they're talking about lots and lots of tiny transistors that are either on or off. When they're on, it's a 1. When they're off, it's a 0. So when you're storing memory, when you're storing things in memory in a computer, you're using transistors that are turned on and off. When you talk about solid-state hard drives, those are like memory. They have a whole bunch of transistors that are turned on and off. So those transistors are etched into tiny silicon chips, and we'll see how that happens later in the semester. But you can fit millions and millions of these transistors in one tiny little computer chip. And when they all work together, they become a processor or memory or things like that. So transistors are the building blocks of all digital technology. They're also the building blocks for pretty much all analog circuits. So they can be used to amplify signals. So they can be used in things like radio receivers, audio amplifiers, op amps, which are little chips that are used to amplify signals coming from instruments and things like that, from medical devices that amplify the signal from your heart. All these chips are based on lots and lots of tiny transistors. So if you want to really understand how those chips work, you have to understand how transistors work. Okay? So they can be used as building blocks. They can also be used on their own. So we can use transistors to control motors, like I said. We can use them to control lights and things like that. We'll see that very large transistors can be used to control things like trains that are moving down the track. So last semester we had a student who worked at Sacramento Regional Transit, and one of his jobs was to change out the transistors in the trains when they went bad. So so those transistors were like this big. They've got a huge heat sink, and we'll talk about those a little bit more in a future lecture. But transistors really have applications all over the place. Okay, so they're hugely important. So that's why we care. Questions about that? All right. Then let's talk a little bit about how they actually work. So transistors are sandwiches of N-type silicon and P-type silicon. So they're made up of, each transistor is made up of 3 blocks of silicon. So there are 2 ways that you can make that sandwich. You can make it like an NPN, so a negative block and then a positive block and then a negative block, or you can make it PNP. And transistors are made in both of these ways.
Yeah, they're made the same way they make the diodes, like we were talking about before, where they mix. What do they mix? I can't remember the.
Yeah, they do doping on the silicon to
doping.
create the N-type and the P-type. Yeah, and the doping is done in exactly the same way. And so, remember, diodes were they just had 2 blocks. They had an N-type block and a P-type block. Now, transistors add 1 extra block over here. So, and then there are wires attached to each block. So this would be an NPN type transistor. And then this is a PNP type transistor. Yeah.
So if you took 2 diodes and put them together, like with a positive and then the 2 negatives out, would it work the same?
Not quite. Oh. Not quite. Because what we'll see is that we put a small amount of electricity in here, and it flows out that way. And then that allows a larger amount of electricity to flow through this way.
Oh, wow.
So you don't have quite the same structure if you just stuck 2 diodes together, because this is it's a sandwich where the 3 blocks are touching each other.
So in water world, it works more like T, right? Cross T.
Like if you were talking about plumbing?
Yeah, like if you think about current or.
Yeah, kind of.
But it's kind of like positive starts, opens the valve, and only then the larger current can go over voltage. something
Yeah.
like that.
Yeah. I think you're thinking along the right lines. Yeah. So, so each type of transistor has a symbol, and they look similar, but there are important differences. So this is an NPN type transistor. And this is a Pnp type transistor. Okay. So there are three terminals, and each terminal has its own name. This is the collector. On an NPN transistor, this is the collector, this is the base, and this is the emitter. On a PNP, this is the collector down at the bottom. This is the base, and this is the emitter. So you'll notice that the emitter is the one that has the arrow pointing on it in both cases. So the arrow is always the emitter. Now, you'll notice on the PNP, the emitter is pointing inwards. On the NPN, the arrow is pointing outwards. So you can, there's a little phrase you can use to remember this. You can think of NPN, you can think of it standing for never points inward. The arrow never points inward on NPN transistors. Okay? Now, we said that the transistor acts kind of like two diodes back to back. So with an NPN transistor, the diodes also never point inward. So this is the collector, base, and emitter down there. Whereas with the PNP transistor, you also have two diodes, but they are facing the opposite direction. So they're both pointing towards the middle. Yeah. So the way that these transistors work is that
Are these Zener
no,
in there?
no, not really. So what happens with an NPN transistor is that when the base voltage is equal to the emitter voltage, there's no voltage across this diode, right? So no voltage is flowing through there, and therefore no current is flowing through there, and so that doesn't allow any current to flow through the rest of the transistor. As a little bit more current as you allow a small amount of current to flow into the base, that allows a large amount of current to flow there. So if we say so if you put a small amount of current in there, into the base, that flows down to the emitter, and then that allows a much larger current to flow from the collector to the emitter. Okay? Yeah.
So does it flow through that diode on the collector side, or is it going around it?
It kind of goes around it. So it doesn't flow from the collector to the base. That would be flowing through the diode. It doesn't go there. It goes around it and goes to the emitter. So that's why you can't just put two diodes
Gotcha.
touching each other. There's this other path around where the large current flows.
So what's stopping it from going across that other path initially? Like, I mean, I understand that you have to put the small current through to let it go
Right.
on that path, but why?
So it has to do with the physics of the diode. So basically, when you put a small amount of current in here, it starts to. So the P type region has all of those holes in it, right?
Yeah.
So you put a small amount of current in there, and it fills up some of those holes, and then that allows some of the electricity to flow across
All right.
there.
That makes sense.
Starter,
Yeah.
right?
What's that?
It works like starter.
Yeah, exactly. Yeah.
Okay.
So, right. So a small amount of current flowing from the base to the emitter allows a large amount of current to flow from the collector to the emitter. So that's how an NPN transistor works. A PNP transistor works. You allow a small amount of current to flow from the emitter to the base, and then that allows a large current to flow from the emitter to the collector.
Oh. Interesting.
Yeah.
So why would you want to use one versus the other? Because it looks like, I mean, both of them you put a small current in to get a large current somewhere. So why?
Small current,
Right.
Same emitter. That's really right.
Well, sometimes you need both types of transistors. So we'll see there are some applications where you can use one or the other. They're kind of interchangeable, and then some applications where you use both of them together. So in the applications where you use both together, it usually looks something like this. You've got a PNP transistor up here, and then an NPN transistor down here. And both of these are hooked to one input signal. This is ground, and then this is VCC. And then over here is the output. So the way that this works is that when you have a low voltage here at the input, that turns on this transistor, and it creates a high voltage at the output. When you have a high voltage here, this one is turned off, but now this one is turned on, and so that creates a low voltage at the output.
Oh, that's cool.
So yeah, so it's called a push-pull arrangement, because half the time one of the transistors is working to create a low voltage, and the other half the time the other one is creating a high voltage. If you had just one or the other, you could create a low voltage on the output or a high voltage, but not both. So sometimes you need both to create both types of outputs. Yeah.
So do they have like pre-made chips that already do that? I'm assuming.
Oh yeah.
Components?
Yeah. So so we'll see in a couple of classes that this is one type of amplifier, and there are amplifier chips that are made specifically for that purpose.
Yeah. That's cool.
Yeah. Yeah, so let's see. So really current controls current, right? A small amount of current going in controls a large amount of current from the collector to the emitter, or from the emitter to the collector. So this is a little bit hard for some people to think about, because oftentimes we think about voltage controlling things, but here it's really a current controlling the current. So each transistor has a gain. So the gain, basically the gain is how much more current you get out than you put in. So current in times gain equals current out. Okay, so let's say we had a gain of 100, and we put in 1 milliamp. How much current would you get out?
A tenth of an amp.
Yeah, 100 milliamps, right? So you put in 1 milliamp, you multiply it by 100, you get 100 milliamps out. So if you put in 5 milliamps, you get out 500 milliamps, right? And that's a pretty typical gain for transistors. They're somewhere usually in the range, from 80 to 300, somewhere in there. Each transistor is a little bit different, though. So you can't really rely on it being exactly 100 or exactly, 150. There are different serial numbers, or different models of transistors, and even within a particular model, there can be variations from one to another. So you can't really rely on exactly what this number is. It's just, it's a big number. Yeah.
To be sure, you need to measure it, to test it.
Well,
I mean, if we're talking about such a thing like electronics, or when you're trying to make something, they're going to count for you, or you want to make sure it's actually
right. So yeah. So actually, typically, what happens is that people design circuits where there is some feedback, and they don't rely on exactly what this number is, because
give some tolerance.
Yeah, there's some tolerance. Exactly. They design the circuit in such a way that it can work well even with a range of values, because the transistors can change their gain even on a single day with a single transistor, depending on how much heat there is and things like that.
Yeah.
So yeah, it's just not a very reliable number. So you just have to understand that it's not reliable and work with that. Yeah.
So it'll say like all that stuff on the data sheet, right?
Yes. Yeah. Exactly. So when you look on the data sheet, it doesn't say just gain, there are two types of gain. So there is HF, they're both called HFE, which is really helpful also. So there's HFE, where the letters are capital, and that is...
Really?
Right, I know. That's the DC gain. And then there's HFE, where the letters are lowercase, and this is, AC gain.
Nice.
Yeah. Yeah, I know. So, yeah.
So do they have different transistors that only work for AC or DC, or do they have some that work for both?
They generally work for both, but they have a slightly different gain
For each one.
for
So
each.
it'll say both in the gains. Okay.
Yeah.
Okay, cool.
Right. So, so that's what's going on there. Let's see. Oh yeah, since these are current controlled devices, you can't hook voltage directly to the base, right? Because the base really is like a, it's like it's attached to a diode, right? And what is the maximum voltage drop you can get across a diode?
0.7.
About 0.7, right? So if you hook a voltage to the base, say you try and hook 2 volts to the base, that's going to destroy this diode, and your transformer is going to be, or your transistor is going to be toast. Okay? So when you have transistor circuits, you have some sort of a resistor between the input voltage and the base. That way, you can make the input voltage high or low, and then if it gets too high, it just gets dropped across the resistor before it gets to the base. So you could have 10 volts over here. The base would still be at 0.7 volts, and then the remainder of the voltage difference would be across that that resistor there. Okay. All right. So that's what I wanted to say about transistors. This is the basic way that they are made. These are some diode models of transistors that work pretty well. So we can take a look at a data sheet for a minute and actually find some of these gains. Okay, so in your book, there are actually lots of data sheets at the end. So some of the most common types of transistors are called 2N3904 and 2N3906. So the 2N3904 is a type of NPN transistor. The 2N3906 is a type of Pnp transistor. Okay. Now, something interesting to notice about the name, you notice that these names start with 2N, whereas the diode names started with 1N. So there was the 1N914 was the common type of diode that we used. So the 1N or the 2N actually refers to how many junctions there are in the silicon. So with a diode, there was one junction, right? There were 2 blocks, so there was one junction between them. With transistors, there are 3 blocks, so there are 2 junctions between blocks. So that's what the 2N means at the beginning of the name. So anyway, 2N3904 is a common type of transistor, and if you look on the table of contents, you can see all of the data sheets listed, and it shows that the 2N3904 data sheet is on page 195.
NPN?
Yep. So the 2N3904 is an NPN transistor. So the data sheet starts on page 195 and it continues on to 196. So if you look on page 196, you should be able to find a listing for HFE, the DC current gain. So that's about a third of the way down. These are in the section listed on characteristics. So you'll notice that there are lots of different values shown there. So anywhere from a minimum of 15 all the way up to a maximum of 300. Okay, so you can tell that there's a wide range of different values that this can take on, even just within a single type of transistor. You know, a single part number from a single manufacturer can have wildly different values depending on conditions and manufacturer. So the way that it was made. So so there you can find some values. There are some other values, I believe, that you're going to have to find when you look at the lab, but now you know how to find the data sheet, and so you can look those up. And this book contains lots of other data sheets as well. So in the lab today, you'll be asked to find information on a number of different parts. You can find the data sheets for most of them in the back of the lab book. There is one that's not in there. The 2N3053 is not in there. For that one, you have to look online. So you can just go online and search for 2N3053 data sheet, and that should be able to pull up a data sheet very similar to what you see here. Okay?
Is there a website that's most reliable for those?
I like to use DigiKey.
DigiKey?
Yeah, digikey.com. They have a lot of data sheets, but there are lots of others as well. There's Mauser, there's Newark, there's a ton of them, and they're pretty much all reliable.
Okay. I was wondering if anyone would like take the data sheets out or something.
I haven't seen anybody.
It wouldn't surprise me.
Right? Yeah, that's true. That's true. I haven't seen any, but it wouldn't surprise me either.
I know.
Yeah, right.
I think you're going alarm clock at the Lee bomb.
Right. Yeah. Okay. Yeah. So there are data sheets that tell you where to find this or what this information can be, you know, a general range, but then you can also use the meter to actually measure the values. So if we're looking at the meter, it has a special location made specifically for measuring transistors.
So you just pump a small current through them and measure the...
Yeah, the gain, exactly. That's exactly what it does. So, you've got the dial right there in the middle, and then down here, there are 4 holes labeled E, B, C, E. Okay? So E stands for emitter, B stands for base, C is collector, and then emitter again. Now you might wonder why they have 4, right? Since we only have 3 legs on a transistor. Well,
Different types.
yeah, exactly, different types.
Yeah.
Right. Each transistor has 3 legs sticking out, but they can be in all different orders. So one might be EBC, the other one might be BCE, the other one might be CBE. They can be rearranged and mismatched and put in any order that the manufacturer wants. So when you are looking at a transistor, you also need to use the data sheet to find out which leg is which. Okay? So when you're doing your lab tonight, it'll ask you to look up the data sheet for each transistor and figure out which leg is which. Okay? Yeah, so depending on how the legs are arranged, you might use the left 3 holes or the right 3 holes. Okay? So, and then this port down here is labeled H, F, E, and the letters are capital. So is it a DC or an AC gain?
DC.
DC.
DC, right. So H, F, E. So over here, there's a little section and it says NPN up here, and then PNP. So you put the meter facing down towards the appropriate type of transistor, and then you put the transistor in there, and then it'll measure the DC gain for you. Okay? So that's how you can measure the gain of the transistor. Sometimes, though, you just need to check whether the transistor is working or not. And you can do that using diode measurements. So there's a diode section on the transistor as well. And that's over here. And what you can do is you can put the meter in diode measuring mode, and then you can hook it up to various legs on the transistor. So if you hook it up from the base to the emitter in the forward biased mode, where you've got the positive lead on the base and the negative lead on the emitter, then you should see how much voltage across that junction?
0.7.
About 0.7 volts, right? If you hook it up in the reverse direction,
Nothing.
you should see, yeah, nothing. You should see overload, okay? So if you don't see those readings, if one of those readings is not like that, then you know that the transistor has been damaged in some way. You can do the same thing from the base to the collector. One way it should show about 0.7, flip it around the other way, and it should show overload. And then between the collector and the emitter, it should always show overload when you don't have any current going to the base, because it should always, there should not be a path from the collector to the emitter. Okay? Yeah.
What is the smallest? Oh, what's the smallest amount of current that you can use to activate one of these guys?
Very, very small.
Does it say, is that also in the data sheets?
I would say what's the biggest, because it's probably uses tons.
Yeah, there is a maximum for sure. I'm not sure. Well, it does talk about small signal characteristics.
Because it has some resistance, that's why it creates a lot of heat, so.
Right.
Kind of pico. Probably.
So they talk about a base cutoff current, and that is listed at 50 nanoamps.
Thanks.
Yeah, so very, very small.
You can breathe on it.
Yeah, so 50 billionths of an amp.
You can grab onto it and the current. Oh.
Yeah, I guess they're right.
Yeah.
Wow, that's cool.
So, Yeah, so that's what's happening here. Yeah, I mean, you're talking about, you know, walking across the carpet.
Yeah.
That is actually a very important thing when you're dealing with transistors, because
ESD.
right, exactly. When you walk across the carpet, you can build up a lot of voltage. And we said that this is a diode, and more than 0.7 volts can cause those diodes to get burned out, right? So when you walk across the carpet, you can get hundreds of thousands of volts on you, and so that's a real issue, a real hazard when dealing with transistors, especially very, very tiny transistors, like the type of transistors that are burned into the silicon in chips. They're very, very sensitive to static, and so when companies are manufacturing them and when they're making chips or certain types of transistors, they take a lot of precautions to make sure that static does not build up.
Everybody's grounded, right?
Everybody, seriously, everybody is grounded. They have carts with rubber straps that drag on the ground, special conductive rubber.
Tables with the mats that you plug into.
Exactly. Yeah, because
Shoe dischargers, hand dischargers.
Little wrist straps.
absolutely. Yeah. So all of those things in order to make sure that you don't build up static, because that can damage these chips. Now the ones that we have in this room are not that sensitive. So, and we don't have a lot of things that cause static around here anyway. So you don't have to worry about that during your labs, but when people are manufacturing these, it absolutely is a big concern. Yeah. Okay. All right, so we've talked about the transistor measuring mode, we talked about how to use the diode measuring mode, and we talked about data sheets. So, in general, for an overview of your lab tonight, basically what you're going to be doing is you're going to be looking at several different types of transistors. You'll look up some information about them in data sheets. You will use the diode measuring mode to check that the diodes are functioning and not broken, and then you will test them using the transistor measure mode to find their actual gains. Okay? So that's what you're going to be doing tonight. So any questions about that? All right. Then you guys are free to take a break, and you can start your lab in just a minute.
Yeah.
All right.